Hey folks, Ms. Gosling here. Welcome to your very last video on magnetism. In this video, we are going to be talking about magnetic forces and motion. And by the end of this video, you will be able to describe the effects of magnetic forces on the motion of different particles. It's a little different from what you're used to. So we're going to start by comparing two equations that you should now be familiar with. The first is our equation for work. And what that equation says is that the work done on an object is equal to the force parallel to an object's motion times the distance an object travels. So if I'm pulling a sled that you're sitting on, I'm pulling it with some force, some distance. So say I'm pulling it, 10 meters to the right, and say that my force is at some angle. The only part of my force that is going to do any work is the part that is parallel to the distance that is traveled. So this whole vertical component of my force does no work. Now, what's interesting is that magnetic fields and magnetic forces are always perpendicular to I, and they were always perpendicular to V. So what that means is my magnetic force is always perpendicular to the motion of particles that are affected by magnetic forces. So what that means is that my magnetic force can never be, there's no component of a magnetic force that is parallel to the motion of an object, and therefore magnetic forces do no work. And that's so important, I'm going to write it down in big caps. Magnetic forces do no work. So what other forces don't do work? Electric forces can do work. Applied forces can do work. Gravity does work for sure. But one category of force that does not involve any work happening on an object is any force acting as a centripetal force. Because remember, centripetal forces are always perpendicular to the motion of an object. What that means is that magnetic forces often act as centripetal forces. So, quite often when a particle is going into a magnetic field, so if I draw a magnetic field, say, coming out of the page like so, and I draw a particle of some kind traveling into that magnetic field, the particle is going to feel a force pointing to the right. And so the path of that particle, instead of being straight and speeding up or slowing down, it's actually the way that magnetic forces are going to act on objects is to cause them to accelerate centripetally to move in a curved path. So what's important to know here is that a magnetic force is not speeding this particle up or slowing it down. What it's doing is causing it to curve. It is causing its motion to curl. So let's take a look at a problem. So example 1, an ion with a charge of 3.2 times 10 to the 19th coulombs. That should be negative 19th, I believe. Let me go ahead and fix that. 10 to the negative 19th coulombs. And a mass of 2.7 times 10 to the negative 26th kilograms is moving due south at a speed of 4.8 times 10 to the third meters per second. It enters a uniform magnetic field of strength 4.6 times 10 to the negative 4th Tesla, directed downward. And we're going to go ahead and highlight south and down as well. Determine the force acting on the ion and draw its path of motion. So let's go ahead and do this. So what I'm going to say is that towards the ground is into the page. And I'm going to go ahead and say that south is down. So what I'll do is I'll go ahead and I'll draw my magnetic field going into the page, so a bunch of X's. then I'll go ahead and draw the motion of my particle before it enters the field, like so. Now, my field is going down, or it's going into the page, and my particle is going down. So by the right hand rule, your finger should be pointing into the page, your thumb should be pointing towards you, so down. And so where the particle is going to feel the force is to the right. So the particle's motion is going to look like this because it's feeling a force to the right. So it's getting pulled farther rightward the more it moves. So that red dotted line is going to be the path of the particle. And I could maybe make that a solid line if I wanted to and write the word v so that I know that it's velocity. So let's go ahead and figure out the force acting on the ion. And I'm going to do that. And to do that, I'm going to go ahead and start listing out my givens. So I know that Q is 3.2 times 10 to the negative 19th coulomb. I know that the mass of my particle is 2.7 times 10 to the negative 26th kilograms. I know that the speed of my particle, v, is 4.8 times 10 to the third meters per second. And I know that the strength of my magnetic field is 4.6 times 10 to the negative fourth Tesla. One thing that I did not mention that I also know is that the particle is perpendicular to, the particle's motion is perpendicular to the path, to the direction of the field. So my angle is 90, and I can use my nice, easy, simple equation. And that I know from my picture. So my unknown here is going to be my magnetic force. So F equals question mark. And the equation I will use, again, is my nice simple one, because my field, or because my particle's motion is parallel, or is perpendicular to my force. So what I can say is that force is equal to QVB, and I'm using this equation because I know Q and V. So instead of having a current, I have a single particle. So let's plug in some numbers. We'll sub and solve. So my force is my unknown, so that can stay. Q is 3.2 times 10 to the negative 19th. V is 4.8 times 10 to the third. And B is 4.6 times 10 to the negative fourth. And I will multiply those all together to get my magnetic force, giving me a final answer of 7.1 times 10 to the negative 19th newtons. And there you have it, guys. My magnetic force is 7.1 times 10 to the negative 19th newtons, and the path of the motion of this particle is going to be a circular path kind of down to the right, drawn up here. So takeaways. Magnetic fields do no work. And as a result, magnetic fields will almost always be acting as a centripetal force. So when you're thinking about the motion of an ion in a magnetic field, you should be thinking that thing's going to be moving in a circle. And so whenever you're asked to draw the motion of a particle in a magnetic field, you should immediately think curve the path. There you have it, guys. This is all I got for you. Best of luck, give it your best shot, and happy solving.